Hi, my name is Vince Jones. I'm a professor of entomology at Washington State University. I work at the Tree Fruit Research and Extension Center in Wenatchee, Washington, working on non-chemical control of insects and mites and biological control in tree fruits. I've been asked to talk about the future of IPM, and so if you look at IPM, it really is a decision-making process, and there's two parts of this. The first is to actually have the science behind it, which enables us to have a framework upon which we base our management programs. And the second is getting that information to the user. IPM is really a philosophy where what you need to do is make decisions one way or another. And those decisions need to be based on a strong theoretical basis. And then that information has to get to the user at an appropriate time. One of the things about IPM decision making is the information needed is very time sensitive, so that if you miss a window in time, you might as well not even have the information because the damage has already occurred at that point. For the future, one of the big problems that we need to address is the fact that we're having declining resources. We have a greater amount of information which needs to be integrated together to get the correct decision. And the public is demanding lower residues on our fruit and more ecologically sustainable long-term IPM type programs. So one of the ways to go about this is to use a strong theoretical basis to make your decisions. And so that is basically a problem in population biology. So what we're looking at is the importance of different species, when they do certain parts of their life cycle, how fast they're doing it, and what the results will be when there's interacting populations. And so what we're trying to do is minimize the impact of our different control strategies on the natural enemies, at the same time maximizing those impacts on the pests. Once you get to the point that you have some sort of theoretical model, what you can do is you can start to evaluate different control tactics. And one of the things that we've been doing at Washington State University is to try to look at how much mortality do we really need to make a big impact on the pest, and how does that need to be applied at different times during the season. Surprisingly, there has not been very good models for pesticide impacts on natural enemies or on pests. And so one of the things that really is surprising when you start running some of these newer generation models is you can actually run them exactly like a pest control program that would be put on the field. So we can vary the intensity of mortality that's occurring, the timing of it, how many times during the season it happens, and evaluate different control strategies for the effects on the pest, and then at the same time run that same model for our natural enemies and see how they're impacted. Because there's no way that you can actually quantify what the effects of the pesticide on a particular natural enemy or a pest are without knowing the time of the season and when that pest population is increasing or decreasing and how much time is left in the season. So basically we're using these models to sort of direct what our management programs will be, or different management programs that we can test in the field. And so, for example, one of the things that we found is that just looking at the model is very simply you can cut the rate of mortality down in half, but if you double the length of the residue of the particular material, you can actually end up with the exact same mortality. And so we can impact the pest just as you would expect with a high mortality type of pesticide for a short period by stretching that out with a lower mortality over a longer period of time. And what this does is allows us to use lower rates in the field and sometimes cause the natural enemies to have less mortality because of the stages that they're in. The other thing about pest management in the future is trying to quantify these pesticide effects is very important, because typically people have focused on direct mortality alone. And what we're seeing is that there are behavioral effects which are actually quite astounding. So some of the newer pesticides that are replacing organophosphates at field rates of, or rates of about 1 to 3% of the normal full field rate, completely shut down the females from ovipositing, calling, or flying. And so essentially we can get the activity equivalent to mating disruption with a very, very low rate of the pesticide and have very minimal effect on some of the natural enemies. But again, it's looking at the selectivity of these materials, which is critical. Once you have this strong theoretical basis, what you need to do is then tie that into some sort of information delivery system. One of the problems that we've had in agriculture, at least in the Pacific Northwest, is the time that we can actually get growers and consultants to come to management programs is very restricted. It's basically from January 1st to the end of February, and then you're expecting them to remember all that information near the middle of the season, maybe 6 months later, on what they're supposed to do. So what we've been able to do in Washington is actually develop a decision support system which addresses all the major pests associated with tree fruits in the state. We're hooked into a weather network of about 140 different weather stations, as well as to Noaa, which has a national digital forecast database which gives us forecasts throughout the continental U.S. on a 1.5 by 1.5 mile grid. And so we can not only run the models to predict when certain events in the life cycle of the insect that are important for management occur, but also give you the recommendations, and then using the NOAA forecast we can actually project that into the future 7 to 10 days. And what this does is it allows us to pull all these management decisions together and give people a warning of exactly when they need to do some sort of management tactic, whether that's sampling, spraying, calibrating their sprayer. Any of those sorts of resources are available on our system. We're also trying to integrate together longer range forecasts. So again, it will make it more of a management type system rather than simply responding to crises. A big part of IPM in the future really has to be focused on these quantitative interactions and the predictability in the different systems. This allows us to scale these to different locations and to make sure that growers are getting information at the best possible way throughout the state at the time they need it. This education system supplement that we've developed is essentially a new communication channel. And the nice thing is with the advances in computer technology, and particularly in the internet and mobile internet, is this information is available at all times 24/7 and is available to them out in the field because the mobile network is now completely throughout the state. The ability to see these predictions and see when different things are supposed to occur really facilitates the ability to do things like sampling of insects, because one of the most frustrating things to do with IPM is when you're sampling and you're not finding anything, and then damage occurs later. And so particularly for some of these smaller stages of the larvae of things like leaf rollers, essentially we can predict when those things should be present and when timing of the sampling should be concentrated. And this has really made a big difference. The other thing that happens with this decision support system is we're able to actually eliminate errors which occur through transmission of information through a long chain of information providers, so that the people that are actually designing these systems are the ones that make the recommendations directly, so that you're not getting misinterpretations that occur through the process of the educational system. Growers typically recognize biocontrol only when it fails. And so all of a sudden they have a huge population of aphids or mites because they're very sensitive indicators of pesticide upset. Because of that, they really do, and the small size of these insects, they often do not have a good way of knowing what the population of the natural enemies are. And so we've been developing monitoring tools for these natural enemies, and these are different chemicals. One can be floral volatiles, which is chemicals given off by the flowers, or it can be what are called herbivore-induced plant volatiles. And these are chemicals that are released by the plant when the insect feeds on the plant and actually causes it to emit a different bouquet of vapors out there. And these are attractive to some of the natural enemies. We've developed some lures which are highly attractive to a range of natural enemies, and the abundance and diversity of the natural enemies is far beyond what we had previously suspected. The agricultural systems are not simple systems. They're very, very complex, and in our systems we're actually finding more than 140 different natural enemy taxa which we have to record at all times. However, that's impossible for a management program to be used in that way. It's a great research tool, so it allows us to develop phenology models which predict when the natural enemies will be present, but it's not very useful from a management standpoint. So what we've had to do is develop tools that are useful for indicator species, that is one or two different natural enemies which are very large, very easy to see, and are highly attracted to our lures. And what this allows us to do is to evaluate sort of the health of the biocontrol complex simply by looking at these 1 to 2 different natural enemy groups. And the two groups that we're focused on are the lacewings and the syrphid flies, both which are predators of aphids, with the lacewings also being predaceous on a wide range of other pests. Having these tools that allow us to see what the natural enemy complex is also allows us to evaluate the different management programs. And so when you compare, for example, a side-by-side orchards, one which is under a very heavy conventional spray program and one that's in a lighter organic spray program, you can see major differences between the pest complex in the different areas, both in terms of the abundance of these key indicator species, as well as, in the research sense, the diversity of natural enemies throughout the season. Our idea is that what we want to do is have the fewest interventions possible that still give a good management program and still good control of the pest. And we can do some of that by altering the timings, altering the rates, and evaluating different management strategies. So overall, I think the major goal of IPM in the future is to try to develop these different areas where we have information gaps, quantify that as well as possible, and then combine it with the new technologies that are available to us and synthesize this information into an overall package that the growers and consultants can access well ahead of time so that they're not surprised by any of these different pest outbreaks, and then try to reduce the residues and the number of interventions that we have in our crops.